Hey YouTube, today we're going to have a quick look at the Jackson Labs GPS disciplined chip scale atomic clock. This device has been sitting on my shelf for quite some time now, and Jackson Labs has been going through great lengths just to get me a evaluation sample of this. You need to understand, after I contacted them more or less jokingly to get a sample of this device, they were more than willing to do that, but the problem was the actual atomic clock part itself is a commercial off-the-shelf part that they buy from Symmetricon. So while they were more than willing to give me a free sample of their product, they would still have to pay for the actual atomic clock. And this is not an atomic clock that you would buy on eBay for $100 out of an old cell phone tower. This is, you know, a military-grade atomic clock. You can buy a car for the price one of those cost. So it appears that Jackson Labs actually went to Symmetricon to get an evaluation sample for themselves. And unfortunately, they did not provide Jackson Labs with a 10 megahertz sample. The normal frequency of the Jackson Labs chip scale atomic clock would be 10 megahertz, but Symmetricon could only provide them with a 10.24 megahertz sample, which was probably a more common value that was used in communication systems. So they actually redesigned the entire software and even did some hardware modifications on the board just so that they could provide me with a free sample. And they didn't even know whether or not I'm going to give them a good review or a really poor review. So that's customer service right there. You know, they had to face the possibility that I would say, okay, this product is totally substandard and I don't recommend it. Yet they went to the great length of actually getting an atomic clock from Symmetricon, changing the software, spending hours making sure that this is really all still functioning, that it's all within specs, and they did all this without even complaining about me taking so long to even get started on a review. That's pretty impressive. Okay, let's talk about what we see on the display right now. Right up here we see that we are currently 0.16 nanoseconds ahead of the UTC second. It looks like we're going to be close to zero and going to be undershooting. Now we're lacking the UTC second by about 0.3 nanoseconds. Just think about that for a second. 0.4 nanoseconds. That's impressive. Down here it says a frequency error rate, and if I understood the manual correctly, 5.75 or now 6.43 means that we're somewhere around having a drift of about 6.4 picoseconds, and that's also pretty tiny. With this little button down here we can actually click through different display options. Here you see the date, so now you know when I filmed this. This is obviously UTC time, 104 UTC. Currently have 9 satellites inside, which is also an impressive value, because what you don't know, I actually have the GPS antenna just clamped to my workbench here. It's not outside. I'm inside in a building with a big roof above, and well, we're sitting next to a window, but even that has shades in front of it, so it's pretty impressive that it locks on the sat no problem. Okay, move on. Now we should play a game and ask, where's Sebastian? Here's my GPS coordinates of my lab. I will probably blur part of that out on the video later just because. Next, I'm 80 meters. I wonder, it's probably above mean sea level. Has to be. So 80 meters MSL. We see the steering value of the CSAC. The alarm value, I honestly don't remember what that was for. Whoops, and I overjumped one. This button sometimes seems to be moody and it just doesn't want to debounce right. Here we go, that's where I wanted to go to. This one actually shows you the current draw, 0.71 milliamps, which is not very much. And that goes hand in hand with Jackson Labs' power consumption promise. They say the power consumption is around 1.4 watts. And that's rated at 25 degrees Celsius and with a 12 volt supply voltage. It's not very much. We see the temperature here in my lab. I don't know, that can't be the lab. It would be a little bit warm. Actually, I'm honestly not certain if it's 33.97 degrees in my room or if that's the temperature of the chip scale atomic clock. I am not certain, but again, I'm sure Jackson Labs will love to clarify this one. Okay, let's go back to this one right here. You see that the values actually change. Obviously, as GPS lock changes, the software tries to really center this time up here around 0. We want to be spot on the UTC second. And that's what the software is trying to do constantly. Now, while we're talking about UTC second, let me actually address something. Even many skilled, old, experienced engineers mess up the difference between accuracy and precision. I very often hear people say accuracy when they actually mean precision, and say precision when they actually mean accuracy. And this has gone so far that most people actually use both terms interchangeably and have no idea what the difference is. So let's talk about that for a second. And this would also explain why we're even GPS referencing this, because think about it for a second. GPS uses a bunch of atomic clocks, right? Yes, correct. We're also having an atomic clock here. So can't we assume that if we would have atomic clocks of equal quality, that it will be redundant locking them to each other? And sure, more atomic clocks, you know, if you average them out, you would probably have a lower error rate. But at the same time, you have things like atmospheric disturbance and other things that influence the GPS signal. So what are we doing here? Well, think about it like two clocks. Let's take two perfect clocks that really between every second, there's exactly 1 second time going by. Let's assume those two clocks have the exact the exact spacing between each second. Yeah, it may still be possible that they are half a second offset to each other. So even though they may have the exact same frequency, they may not necessarily be absolutely synchronous. And for telecommunication applications, let's take frequency hopping spread spectrum for instance as an example. You need absolute 100% accuracy and precision. And accuracy is how close your signal is to a known reference. In this case, we're referencing to the UTC second. Okay, so there's a 1 pulse per second output here, and more or less this top line indicates how far there is an offset between the UTC second that's officially been given by the National Institute for Standards and Technology and this. At the moment, we are lacking about 1.63 nanoseconds. The other side is the precision. What is the real spacing between our seconds? Are they really seconds, or are they a little bit off? Okay, we could be spot on the first second pulse, but then we could be losing it down the line. That would be precision. It's more or less, if I repeat something, how often will it be close to the first shot that I had? That's precision. It's kind of like a gun. You want it to be more precise than accurate, because if it always shoots close to the same point, you can correct for accuracy. You can do that by adjusting your scope, or you can even do this by just simply shooting more to the left or to the right, depending on where your gun tends to shoot to. But if you have a gun that shoots close to where you point, but sometimes up, sometimes down, sometimes a lot left, sometimes a lot right, you know, you can't correct much for that because it's more or less random. So often in electronics we try to prefer precision over accuracy and then correct by some means to get the accuracy that we want. Okay, now the next question, if we reference our signal to GPS, if we tune the chip scale atomic clock to the GPS signal, why do we even need the chip scale atomic clock? I mean, the GPS satellites have an atomic clock standard, and we get the accuracy we want, so what do we even need the atomic clock for? Well, the answer is actually very simple. It's what happens if I lose GPS lock. And this might happen rather quickly. You know, bad weather situations may be an example. In a military situation, that may be that intentional jamming or unintentional interference may occur. There may be several reasons why we lose GPS reference. So these atomic clocks here, this whole circuit, once it's been locked, if I would disconnect the GPS antenna, it would have a very, very, very great accuracy and precision in regards of holdover. It's actually insane what these little atomic clocks can do. It's crazy. And another thing is, this here, some viewers of my blog may have seen this before. This is also a Jackson Labs GPS disciplined oscillator, but the difference is this one has a temperature compensated oscillator as adjustable element. Now, like any crystal, those are relatively sensitive to movement and shock. So if I flip this board upside down, this will actually give you a change in frequency of some sort that has to be corrected for. Same with G-forces that you may have in a fighter jet, for instance, influence crystals quite a bit. An atomic clock is not really all too sensitive about any G-forces, and if I understand this correctly, this board has an option to actually get a three directional sensor on there to measure G-force influence on the atomic clock and mathematically correct for error. It's also pretty impressive and very important for high-speed military applications where shock or other reasons for G-forces may be predominant. This ship-scale atomic clock really has a bunch of interfaces. Of course, you see the LC display up here. You got the GPS antenna input here. The board also provides power to the antenna, so you can use an active antenna. You have an RS-232 output there. At the same time, you have a USB port that also emulates an RS-232 port, so you can use either. The board does take Skippy commands. Standard Skippy commands. There's actually a huge documentation for this board about what Skippy commands you can use. The GPS board is right down here. Obviously, this is the ship scale atomic clock itself, and you got some buffers up here. And here you got 1 PPS output. It means 1 pulse per second. You got 1, 2, 3, 4. Normally 10 megahertz outputs, but remember in my case they're 10.24 megahertz outputs. Normally they're 10 megahertz though, remember that. This is probably the only 10.24 megahertz chip scale atomic clock from Jackson Labs in the entire world that exists, okay? That's the only one that exists in my hand, so remember mine is a little bit different than the one that you'd buy. And down here you actually have a divide by 2 rectangular output. So those 4 outputs here are a sine wave, filtered sine wave, and this one here gives you a rectangular wave with half the frequency. So you had 10 megahertz up here, this one would have 5 megahertz. We will actually look at the jitter performance of this output here in a second, since I happen to be lucky to have a Teledyne LeCroy WaveRunner 640ZI oscilloscope sitting around here with a jitter analysis software option. Alright, well, that concludes a quick look at the Jackson Labs chip scale atomic clock. I hope you guys liked it. Now let's move over to the jitter measurement. And I just happen to have this Teledyne LeCroy WaveRunner 640ZI 4 gigahertz oscilloscope sitting on my bench. And while a 4 gigahertz oscilloscope is definitely absolute overkill for looking at a 10.24 or 5.12 megahertz signal, it comes with a wonderful option called Jitter Kit. And the Jitter Kit is a software option available for most upper-class LeCroy oscilloscopes that allows you to do automatic jitter measurements. And this is what you see right here on the screen. Up here you got the input waveform. It's coming from the ship scale atomic clock's divide by 2 output, so we expect to see a 5.12 megahertz signal. And as you can see down here, it is indeed 5.12 megahertz. Up here is the jitter track. It tracks the jitter between every edge that's analyzed up here. And up here is a histogram of the jitter of all samples that we've taken. And I had this thing running for a long while now. You see down here that for the frequency we had almost 800,000 samples, and down here for the rise time we almost have 1 million samples in the entire time it was running so far. And Mr. Gauss himself would be very proud of this curve up here. It looks like a near perfect Gaussian distribution. And I hope the camera actually focuses well enough for you to see the values down here. If not, I will actually overlay the video with a image later. And let's actually take a screenshot, save it to my USB drive. There we go. Okay. By the way, down here you would normally see a spectrum of the jitter, and I have not properly set that up because I simply don't care about that value right now. Okay, down here we see a period of 195.31245 nanoseconds. We see a frequency of 5.12 megahertz even. A cycle-to-cycle jitter of -85 femtoseconds. Duty cycle 50.235%. A rise time of 386.25 picoseconds. And a fall time of 661.14 picoseconds. We don't really care about fall levels, we only care about rise time. And we see the standard deviation right here is 33.48 picoseconds. That's a pretty impressive score. Same up here. The frequency, the standard deviation is 147.79 hertz. The peak-to-peak deviation that we had is 2.2. Let's round it to 2.3 kilohertz. You know, that's almost nothing. It's very impressive. Same with the jitter here. Peak-to-peak deviation 144 picoseconds. It's a really small number. And that makes me wonder, what jitter performance are we actually measuring here? Are we measuring the phase noise and jitter performance of the ship scale atomic clock? Or of the oscilloscope's timing reference? Because naturally you have to ask. On one side we're having a ship scale atomic clock that's GPS locked and disciplined, and over here we have an oscilloscope that has some sort of free running oscillator on the inside. I don't know what it is. It's probably a temperature compensated oscillator, maybe an oven controlled oscillator, but it's most definitely not an atomic clock standard or anything GPS locked. I wanted to actually hook up my external 10 MHz reference that I have from another Jackson Labs module, but I couldn't do that because it turns out you need a special adapter to hook up your external reference to this L-bus connector down here. And I'm not sure if this is standard or if it's an option that you need to buy from Teledyne LeCroy. All I know, it wasn't in the box of the oscilloscope, so I don't have one. I couldn't do that, obviously. But I think this is an interesting view of the jitter kit itself, and it has numerous options to set up. I didn't really mess with it all too much. I just went into the analysis, jitter kit, and used all the standard settings. You do have a source set up. You can set your percentages that you want to set. So obviously we're using 80 to 20% and not 90 to 10, which you would normally use for determining rise time and things like that. You can set this all individually here. You can set your gating as you please, your measurements, how you would like to display them. You can add measurement, you can remove measurements. You can do all kinds of crazy things with this oscilloscope. This oscilloscope also has MATLAB options. That means you can take any of these tracks right here and apply the values to MATLAB script and have the results displayed on the display. It's pretty cool. Also up here, what I forgot to mention, let's see, we should be able to zoom in here. Oh no, I don't want to mess with that. It's probably going to toss off my entire screen. But, well, oh no, never mind. Hang on a second. I would like to zoom the jitter overlay. No, that was the wrong button, obviously. Let's try that again. Okay. Zoom all selected. And, okay, it's displaying that in the same window here. I don't want that. No, I don't have a keyboard attached, so I can't say undo. But oh well. This was a nice quick oh, there's an undo button. Joy oh joy, isn't this just cool? Unfortunately, this kicked off all my my values that I had here previously, and it actually restarted acquiring data. So down here we see how the samples are being acquired. We now have almost 800 samples here, and you see there are different sample values for each acquisition. It's very interesting to see that. Well, that's a nice overview of the jitter kit. As I said, it comes with many of the upper class Teledyne LeCroy oscilloscopes as an option. My 4000 series HTO doesn't have it, but it's available for the 6000 series, and it definitely shows us that this chip scale atomic clock has a pretty awesome jitter performance. But again, I'm not sure if we're even getting close to measuring the jitter performance of the atomic clock, or if we're actually more so measuring the jitter performance of the oscilloscope.